Hey friends, today we will revise chemistry of class 12. Okay. Chemistry revision we will do for NEET. Okay. We are going to start the solid state. Okay. General characteristics of solid state. Solids have definite mass, volume and shape due to the fixed position of their constituent particles. Solids have short intermolecular distance and strong intermolecular forces. The constituent particles of solid atoms, molecules or ions have fixed position and can only oscillate about their mean positions. Solids are incompressible and rigid. Amorphous and crystalline solids. Amorphous and crystalline solids. Property: crystalline solid and amorphous solid. Property of crystalline solid is shape, definite characteristic geometrical shape, melting point, melt at a sharp and characteristic temperature. Cleavage property: when cut with a sharp edge tool, they split into two pieces and the newly generated surface are plain and smooth. Heat of fusion: they have a definite characteristic heat of fusion and isotropic. Physical properties have different values in different directions. Nature: true solids, order in arrangement of constituent particles, long range order, and isotropic. True solids or crystalline solids are anisotropic in nature. Amorphous solids, irregular shape, gradually soften over a range of temperature. When cut with a sharp edge tool, they cut into two pieces with irregular surfaces. They do not have a definite heat of fusion. Isotropic. Physical properties have same values in different directions in nature. Pseudo-solids or supercooled liquid, only short range order. Isotropic. Amorphous solids are also called isotropic or pseudo-solids or supercooled liquids. And crystalline are true solids or having long range order and they are anisotropic in nature. Crystalline solids are anisotropic and amorphous solids are isotropic in nature. Classification of crystalline solids on the basis of nature of intermolecular forces. Types of solids, type of forces, properties and examples. Ionic solids, lattice points are occupied by positive and negative ions held together by strong coulombic or electrostatic forces. Properties: high lattice energy, hard but brittle, high melting and boiling points, insulators in solid state but good conductors in molten state and in aqueous solutions. NaCl, MgO, ZnS and CaF2. Covalent or network solids. Lattice points are occupied by atoms held by a network of covalent bonds. Extremely high melting points, very hard and brittle. Insulator except graphite. Having graphite have sp2 hybridization. Diamond, quartz, SiO2, SiCalN and graphite. Metallic solids. In metals, the array of lattice points is occupied by positive ions. The outer electrons are loosely held. Hard but malleable and ductile. Fairly high melting points. Good conductors of electricity in solid state as well as in molten state. All metals and alloys are metallic solids. Molecular solids, polar, nonpolar and hydrogen bonded. Lattice points are occupied by molecules and are held together by weak van der Waals forces. Soft, low melting points, insulators. I2, solid, CO2, HCl and H2O. So there are four types of solids, that is ionic solids, covalent or network solids, metallic solids, molecular solids, polar, nonpolar and hydrogen bonded. Okay. And ionic solids are insulators in solid state. Now crystal, lattices and unit cells. A regular three-dimensional arrangement of the constituent particles of a crystal in space is called crystal lattice. Unit cell is the smallest portion of a crystal lattice which when repeated in different directions generate the entire lattice. A unit cell is characterized by 6 parameters, that is 3 edges A, B and C and angles between the edges alpha, beta and gamma. Types of unit cells: primitive unit cells and centered unit cells. Primitive unit cells. Constituent particles are present only at the corner positions of a unit cell. Centered unit cells. Unit cells contains constituent particles at corner as well as other positions. Centered unit cells are of three types, that is the body centered, face centered and edge centered. Body centered. One constituent particles at body center besides the other that are at its corner. Face centered. One constituent particle present at the center of each face besides the one that are at the corners. Anti-center. One constituent particle present at the center of any two opposite faces besides the one that are at corners. Now, 7 primitive cells, unit cells or crystal system. You can learn it by CTORHMT. The trick is CTORHMT. CTORHMT. That is cubic, tetragonal, orthorhombic or rhombic, monoclinic, hexagonal, rhombohedral or trigonal, triclinic, most asymmetrical or unsymmetrical. In cubic, most symmetrical, which is axial distance or edge length, axial angles and examples. A equal to B equal to C, alpha equal to beta equal to gamma equal to 90 degree, Cu, Zn, S, KCl and NaCl. In tetragonal, A equal to B not equal to C, alpha equal to beta equal to gamma equal to 90 degree, Sn, white tin, SnO2, TiO2 and CaSO4. Rhombohedral or rhombic, A not equal to B not equal to C, alpha equal to beta equal to gamma equal to 90 degree. Rhombic sulfur, KNO3 BaSO4. Monoclinic, A not equal to B not equal to C, alpha equal to gamma equal to 90 degree and beta not equal to 90 degree. Monoclinic sulfur, PbCrO4 Na2SO4.10H2O. Hexagonal, A equal to B not equal to C, alpha equal to beta equal to 90 degree, gamma equal to 120 degree. Graphite, ZnSCdS. Rhombohedral or trigonal, A equal to B equal to C, alpha equal to beta equal to gamma not equal to 90 degrees. CaCO3 calcite and HGS cinnabar. Triclinic, most unsymmetrical, A not equal to B not equal to C, alpha not equal to beta not equal to gamma, which is further not equal to 90 degree. K2Cr2O7 CuSO4.5H2O H3BO3. Okay, so learn it by CT or HMT. So you will find a symmetry, that is A equal to B equal to C in cubic, and in triclinic what you can see, A not equal to B not equal to C. Okay. Now, Bravais lattices. The 14 lattices corresponding to 7 crystal system. 14 lattices and 7 crystal system. Calculation of number of atoms per unit cell. Unit cell, simple cubic, body center cubic and face center cubic. Number of atoms and their contributions per unit cell. At corners 8 into 1 by 8. At face in simple cubic 0. And in center there is 0. Total number of atoms per unit cell in simple cubic is 1. And now, body centered cubic 8 into 1 upon 8. At faces 0. In center 1. So total 2 in body center cubic. Z equal to 2. Okay, now face center cubic. At corners 8 into 1 by 8. At faces there are 6 faces. So contribution is half. So what we do is 6 into 1 by 2, which gives 3. So total is 4. 3 plus 1, that is 4. Face center 4, body center 2 and simple cubic 1. Close packing in crystals. Hexagonal close packing HCP, that is AB type. So you can learn it by Hindustan times, that is H and T. Hexagonal, tetrahedral, MZ and Zn. Tetrahedral. Cubic close packing CCP or face center cubic FCC, ABC type. Octahedral. Okay. AG and CU are the example. Cubic close packing CCP or face center cubic ABC type. AG and CU, octahedral. Both these types of close packing are highly efficient with percent occupied space equal to 74 and have coordination number of nearest neighbors is 12. In hexagonal close packing, in CP, what we see is AB type of arrangement, and they are tetrahedral. Examples are MG and ZN. And in CCP and FCC, what we see is ABC, and octahedral, and AG and CU. Now simple cubic unit cells Z equal to 1, A equal to 2R, R equal to A upon 2. Packing efficiency 52.4%. Coordination number is 6. And face center cubic or cubic close packing Z equal to 4. And R equal to A upon 2 under root 2. Packing efficiency is 74%. Coordination number is 12. Body center cubic Z equal to 2. R equal to under root 3A by 4. Okay. Packing efficiency 68%. Coordination number is 8 for body center, face center 12, and simple cubic is 6. Packing efficiency for simple cubic is 52.4, and face center is 74%, and body center is 68%. So they will ask how much space is vacant. So what you will do is just subtract, that is the 100 minus the space occupied or packing efficiency. Okay. Tetrahedral void. In a simple triangular void surrounded by 4 spheres in CCP, tetrahedral voids are located on body diagonals, 2 on each. Octahedral void. In a double triangular void surrounded by 6 spheres in CCP, tetrahedral voids are located at body center and edge center. Tetrahedral voids are present at body center and edge centers, and tetrahedral voids are at body diagonals, 2 in each. If n is the number of closed packed spheres, then the number of octahedral voids generated is n. If the number of closed packed sphere is n, then the octahedral numbers remain same, that is the n. But tetrahedral voids is multiplied by 2. That is, the number of tetrahedral void generated is 2n. And contribution at edge is 1 upon 4 into 12 you will do. Radius ratio of tetrahedral void is 0.225 R. Radius of octahedral R upon R equal to 0.225 for tetrahedral, and R upon R for octahedral is 0.414, where R is the radius of the spheres in closed packing. Radius ratio rules. For the stability of an ionic solids compounds, each cation should be surrounded by maximum number of anions and vice versa. For maximum electrostatic force of attraction, radius ratio R plus radius of cation R minus radius of anion equal to R plus upon R minus. Okay. Now, when the radius ratio lies between 0.155 to 0.225, then coordination number is 3, and structural arrangement is planar structure. Example is B2O3, boron trioxide. And when the radius ratio lies between 0.225 to 0.414, coordination number is 4. Structural arrangement is tetrahedral. Example is sphelerite ZnS. When the radius ratio lies between 0.414 to 0.732, coordination number is 6. Structural arrangement is octahedral, and example is rock salt or NaCl. And when radius ratio lies between 0.732 to 1, coordination number is 8, and structural arrangement is body centered cubic, cesium chloride CsCl. Calculation involving unit cell dimension. Density equal to Z into M upon Na into A cube, and into 10 to the power minus 30 gram per centimeter cube, where Z equal to number of atoms per unit cell. Z is 2 for BCC, 4 for FCC. Edge length in picometer, density of solid M equal to molar mass, and Na is Avogadro number. In imperfections in solid, any departure from perfectly ordered arrangement of constituent particles in a crystal is called imperfect or defect. The defects are of two types: point defects and line defects. Point defects are the irregular or deviation from ideal arrangement around a point or atom in a crystalline solid. and line defects are the irregularities or deviations from ideal arrangement in entire row of lattice points. Type of point solids. Stoichiometric defect. These are the point defects that do not disturb the stoichiometry of the solids. They are also called intrinsic or thermodynamic defects. In non-ionic solids, vacancy defects. Some of the lattice sites are vacant, decrease the density of the substance. Interstitial defect. Some constituent particles, atoms or molecules occupy an interstitial site, increase the density of the substance. In ionic solids, Frankel defect or dislocation defect. Frankel defect is also called dislocation defect. The smaller ion, usually cation, is dislocated from its normal site to an interstitial site. It does not change the density of the solid and is shown by ionic substances in which there is large differences in size of ions, that is ZnS, AgBr, AgCl, Agi, due to small size of Zn plus 2 and Ag plus ions. Schottky defects. Equal numbers of cations and anions are missing. It decreases the density of the substance and is shown by ionic substance in which cation and anion are almost similar sizes. Examples are NaCl, KCl, CaCl and AgBr. AgBr shows both Frankel as well as Schottky defect. AgBr shows both Schottky and Frankel defect. Impurities defect. Second type is impurity defects. Foreign atoms are present at the lattice sites in place of the host atoms or at vacant interstitial sites. When SrCl2 is added to NaCl, two Na plus ions are replaced by one Sr2 plus ion, producing one cation vacancy. This is type of impurity defect. Non-stoichiometric defects. When the ratio of the cation to anion becomes different from that of indicated by the ideal chemical formulas, the defects are called non-stoichiometric defect. There is disturbance in non-stoichiometric defects. Metal excess defects. Metal excess defect due to anionic vacancies. On heating crystals of NaCl in presence of Na vapor, some anion, that is chloride, leaves lattice sites which are occupied by electron called F centers, giving color to crystals. This is due to anionic vacancies. Due to presence of extra cations at interstitial site, on heating, white ZnO turns yellow as it loses oxygen and zinc plus ions, and the electrons occupy interstitial sites. In anionic defects, what we get is color and presence of extra cation, loses oxygen and Zn2 plus ions, and the electron occupy interstitial site. Schottky and Frankel defect is shown by both AgBr. AgBr shows both Schottky and Frankel defects. Due to presence of extra cations at interstitial site, white ZnO turns yellow because of loss of oxygen and electrons occupy interstitial site. Due to anionic vacancies, NaCN in presence of Na vapors when heated, some anions, that is chloride, leaves lattice sites which are occupied by electrons called F centers, which give color to the crystals. This all is due to metal excess defect. Metal excess defect is of two types, due to anionic and due to cations. Okay. Extra cations present in the interstitial site and when anions are due to anionic vacancies. Now, this was about metal excess defect. Now we will see about metal deficiency defect. Usually occur due to missing of a cation from its lattice site and the presence of a cation having higher charge in the adjacent lattice. Example, in crystals of FeO, some Fe2 plus cations are missing and the loss of positive charge is made by the presence of required number of Fe3 plus ions. Example is Fe0.960 and Fe0.980. So you can calculate the numericals by the formula 2 and the percentage given, that is 0.96 or 0.98. So just what you do is 2 into 0.96 minus x plus 3x equal to 2. 2 0.96 minus 3 minus x plus 3x equal to 2. 2 0.96 minus x plus 3x equal to 2. 2 0.96 minus x plus 3x equal to 2. Classifications of solids on the basis of their conductivities. Conductors having conductivity range 10.4 to 10.7 ohm per meter. Insulators having very low conductivities ranging between 10 to the power minus 20 to 10 to the power minus 10 ohm per meter. Semiconductors having conductivity in the intermediate range from 10 to the power minus 6 to 10 to the power 4 per ohm per meter. Conduction of electricity in metals. Metallic conductors conduct electricity through movement of electrons. Atomic orbitals of metal atoms forms molecular orbitals which are very close in energy and form a band. In metals, there is a partial overlapping between filled valence band and empty conduction band. Thus, electrons can flow easily under an applied electric field and a metal shows conductivity. In insulators, the gap between the field valence band and the conduction band is large. Electrons cannot jump to and hence substances have very small conductivity. Okay. Conduction of electricity in semiconductors. In case of semiconductors, the gap between the valence band and the conduction band is small. Some electrons may jump to conduction band and show some conductivity. Electrical conductivity of semiconductors increases with rise in temperature, since most electrons can jump to the conduction band. Doping. It is a process of adding an appropriate amount of stable impurities to increase the conductivity of intrinsic semiconductors. By doping with electron-rich impurities. Group 14 elements like Si or Ge with group 15 elements like P and As, free electrons become available which increase conductivity. Such solids are called N-type semiconductors. By doping with electron-deficient impurities. Group 14 elements like Si or Ge with group 13 elements like boron, aluminium or gallium. As a result, holes are created. Electrons move to occupy the holes. Thus, holes move towards negatively charged plate as if they carry positive charge. They are P-type semiconductors. Holes carries positive charge. When you dope with electron-deficient elements, then it will give P-type semiconductors, and when you will dope with electron-sufficient or electron-rich impurities, then they will give N-type semiconductors. Okay. Classification of substances on the basis of magnetic properties. Paramagnetic substances are weakly attracted by magnetic field. They have one or more unpaired electrons and lose their magnetism in absence of magnetic field. O2, Cu2 plus, Fe3 plus, Cr3 plus. They are having unpaired electrons and they are weakly attracted by the magnetic fields. Okay. Diamagnetic substances are weakly repelled by a magnetic field. They have no unpaired electrons and have zero magnetic moment. H2O, NaCl and C6H6. H2O, NaCl and C6H6 are diamagnetic in nature and there are no unpaired electrons. So magnetic moment is zero. Ferromagnetic substances are those which show permanent magnetism even in absence of magnetic fields. As when placed in magnetic field, their unpaired electron or magnetic domains get permanently oriented in one direction. FeNiCO, Gd and CrO2. CrO2 is ferromagnetic in nature. Anti-ferromagnetic substances are those which are expected to possess paramagnetic or ferromagnetic but actually have zero net magnetic moment due to equal number of domains in opposite direction. Example is MnO. Anti-ferromagnetic substances MnO Ferromagnetic substances CrO2. Diamagnetic substances are H2O, NaCl and C6H6. And paramagnetic substances O2, CO2 plus, Fe3 plus and Cr3 plus. Ferrimagnetic substances are those expected to have large magnetism but actually have a small net magnetic moment due to unequal number of domains in opposite direction. Example is magnetite Fe3O4, ferrites like Mg Fe2O4 and Zn Fe2O4. These substances lose ferromagnetism on heating and become paramagnetism. So ferrimagnetic substances example is magnetite Fe3O4 and anti-ferromagnetic substances MnO and ferromagnetic substances CrO2, diamagnetic substances H2O, NaCl and C6H6. Paramagnetic substances are O2, Cu2 plus, Fe3 plus and Cr plus 3. Okay, all the best.